Hey, I'm Saksham, and I'm a second year PhD student at UT Dallas, and I will present our work Diff-SAGe end-to-end spatial audio generation using diffusion models. Um, this research was done during my internship at Dolby in summer 24, and I'm thankful to all my co-authors for all the help and contributions to this work. Spatial audio plays a crucial component in creating immersive experience, and its demand has been rapidly growing in AR, VR, films, music, and gaming. However, capturing high-quality spatial audio remains a challenge due to the need for expensive equipments and complex recording setups. Thus, spatial audio generation serves as a compelling alternative. Traditional approaches rely on multi-step process, first identifying a desired sound and then spatializing it by panning mono audio to the target location using simulation methods or interactive softwares. However, these methods have several limitations. They require expertise, making them inaccessible to non-experts. Their sequential nature assumes an artificial separation between semantic and spatial content, and they are difficult to scale for tasks like video to spatial audio generation due to their need for manual intervention. To overcome these challenges, end-to-end spatial audio generation presents a promising solution. By jointly modeling spatial cues and content information, it can generate spatial audio directly, eliminating the need for iterative and interactive adjustments. In this work, we formulate end-to-end spatial audio generation as the task of generating first-order ambisonics given a sound class and a spatial target location. Unlike mono audio generation, this task requires producing multiple channels that not only capture the semantic properties of the sound, but also maintain inter-channel coherence to accurately represent the source spatial position. Before diving into our approach, I would like to provide some background. Ambisonics is a spatial audio format that encodes the 3D sound field's directionality into four channels: W, X, Y, and Z. The W channel captures the omnidirectional component, while X, Y, Z represent directional components along their respective axes. This encoding enables flexible spatial audio rendering across different playback setups. Flow matching is a recent generative method framework that has achieved state-of-the-art performance across various domains. It operates by linearly interpolating between noise and target data, and during training, the objective is to learn the velocity field that maps noisy data to its corresponding target distribution. At inference, this learned velocity guides the transformation from any noisy input to the desired output, in our case, spatial audio. And this is how our overall approach looks like. Our initial analysis revealed that straightforward extension of mono audio generation methods to spatial audio generation is not feasible. This is mainly because mono audio generation methods typically operate on magnitude spectrograms and rely on vocoders to reconstruct phase information. However, this phase information is crucial for spatial audio, and vocoders fail to accurately reconstruct the inter-channel phase relationship necessary for spatialization. To address this, we represent first-order ambisonic using complex spectrograms. Specifically, each channel is decomposed into real and imaginary spectrograms, which are then stacked to form a eight-dimensional first-order ambisonic spectrogram. So four channels and each has two components. Our training consists of learning conditional velocity. We first construct a unified conditional representation by encoding multiple conditions, class, azimuth, and elevation using a multi-conditional encoder. We adapt a diffusion transformer-based architecture for audio spectrograms. This model integrates the unified condition into the network using adaptive layer normalization for conditioning. During inference, we imply and an ODE solver for progressively transforming noise into the target FOA spectrogram guided by the input conditions. The generated spectrogram is then converted back into waveform using inverse STFT. Next, we present generated examples on Reaper DAW and the sound field by Rode plugin. And the left side shows the top view while the right side displays the side view, and also we show the angle convention used to visualize it. So for this first set of examples, we kept the class and elevation fixed at 0 while varying the azimuth. The result demonstrates that our model effectively generates high quality spatial audio accurately following the source position as the azimuth changes. In the next set, we show examples where the elevation is changing and the azimuth is kept fixed, and the class is also kept fixed. And additionally, we provide several randomly selected examples along with their respective input conditions to highlight the model's generation quality. Finally, we present a quantitative comparison of our approach against three baseline across two datasets. Our results indicate that our model better aligns with input conditions and generalizes well to unseen test data, demonstrating its effectiveness in the end-to-end spatial audio generation task. Thank you, and here are the project page and paper link.